Hi, so in this video, we are going to kind of reintroduce solutions, which you have learned about in Chem 161, but now in Chem 162, I want us to sort of look at them a little bit more closely, right? Especially applying some of the things that we've been learning about in the previous chapters and seeing how that can enhance our understanding of solutions. But so just to give a quick refresher before we get started, right? Remember that solutions are homogeneous mixtures, meaning that you have two or more distinct chemicals that are not chemically combined or bonded to one another, but instead are physically mixed. And so they don't have any like chemical bonds between them, but they may have certain, intermolecular forces and things that we've kind of seen in the previous chapters. But in a solution, right, you basically have at least two components within it, right? You have a solvent, which is the majority of the solution, and then you also have the solute, which is the substance that is being dissolved. So on the right here, I have a figure of sort of just a classic cartoon of an ionic compound dissolved in, say, water, right? In this case, the ionic compound has dissociated, but it is defined as the solute. The water then is the solvent, right? It's making up the majority of the solution. So in general, the physical state of the solution is kind of dictated by whatever its solvent is. A lot of the times we just immediately assume that solutions are liquids, but solutions can actually be made up of like all states of matter, just depending on what the major component is. Take, for example, gas solutions, like the air that we breathe, right? That is made up of a whole mixture of different gases like oxygen and nitrogen and carbon dioxide and a whole bunch of other things, right, make up the air that we breathe. And that is inherently like a homogeneous mixture because the gas molecules can't be like, I guess, distinguished by any barriers, right? That's what makes something homogeneous versus heterogeneous. Heterogeneous mixtures kind of have like a divide between their components. In a homogeneous mixture, there is no divide there. You can also have solid state solutions. For instance, alloys are like metal solutions in a way. As you guys learned about with metallic bonds in the last chapter, right? Metals don't actually have like chemical bonds holding the atoms together. It's more just like a sea of electrons that are bonding them. And so because of that, if you have, say, some copper and some zinc in a mixture together, it is in fact a mixture. It's not a new chemical composition. So, right, if you ever heard of the word alloy before, an alloy is just a mixture of metals. So take here, brass is not a distinct chemical. Instead, brass is made up of zinc and copper atoms metallically bonded together, so making some kind of solution there. But traditionally, right, the solutions that we focus on, especially in this class, are aqueous solutions, right? Think of water as our solvent and just kind of mixing other things in there. We will explore some other solutions that are not aqueous, but instead maybe have some other solvents. But generally speaking, we're focused on the liquid solvents, so the liquid phase solutions. Now, not all solutions are made equally, right? And so one of the sort of defining factors of a solution or a mix of solute and solvent is the solubility for that mixture. So solubility is defined as like how much solute you can fit into a set amount of solvent. Take, for example, a salt solution. So taking sodium chloride or NaCl and dissolving that into water. There is like a maximum amount of NaCl that you can put into water. If I have 100 milliliters, like just a cup of water, I can add to it 39.12 grams of sodium chloride if I'm at 100 degrees Celsius. So I'm very specific there because solubility can vary depending on the temperature at which you're making the solution or what substances are kind of making up the solution, right? If you change the solute or you change the solvent, you're going to see varying solubility then. So for instance, right, we can change the solute and compare silver chloride being dissolved in water. For that same 100 milliliters of water at that same temperature, I can only dissolve 0.0021 grams of silver chloride. So right, that's a much lower solubility there, and that's just because of kind of what interactions are taking place between the solute and the solvent solvent, which we'll explore a lot more later in the chapter. We can also compare, right, the effect of temperature here. So for, again, sodium chloride, if you want to dissolve that at 25 degrees Celsius instead, you're going to see a slightly lower solubility. Or if I were to try to dissolve sodium chloride in methanol, another liquid, instead of water, I'm going to see a different solubility from that as well. But right, solubility is really varied and it's very distinct for each mixture composition as well as the conditions that they're under. But we're going to look a lot deeper into that later in the chapter of kind of why these differences occur, right? Why we see this increase or decrease in solubility, and really be able to explain those differences using some of the things that we've applied in previous chapters, like intermolecular forces and the likes. So to give us a little bit more language to use to describe solutions and whether or not something is like truly soluble. So right, if you have a solute and you dissolve it into the solvent, if it dissolves well, then your resulting mixture is what we call miscible, meaning that there are no visible boundaries between them. This is basically just another word for homogenized, but we just like to use it especially for liquid to liquid solutions. The way that I remember what miscible means is like really stupid. I say that the divide between the solute and the solvent is so small that it's missable, right? You would miss it. But so the counter to that would be immiscible then, right? This is like if you have a solute and a solvent that aren't mixing together really. So a good example of that would be like oil and water, right? If you've ever tried to mix those two, the oil forms a distinct layer on top of the water, and we call that then an immiscible mixture, right? So this is just kind of basically another way to describe like homogeneous versus heterogeneous, right? Where homogeneous true solutions are miscible, heterogeneous mixtures are immiscible. All right, as we saw with the differences in solubility, certain combinations just have higher solubility than others, and that can be sort of understood by this statement of like dissolves like. What this means is that, right, if you have your solute and your solvent that are similar to one another, right? Maybe they experience similar types of intermolecular forces, like they're both hydrogen bonders or things like that, right? Then because they are similar or alike, right, they're going to dissolve one another. For instance, alcohol that people of age may drink is made up of a mixture of ethanol and water primarily, along with a whole bunch of other things. But right, the ethanol is an alcohol, and so it has that OH group on it, which can hydrogen bond. Water also has O to H bonds, so it can hydrogen bond as well. And so, right, that kind of allows then that mixture to be very homogeneous, very miscible, right? And that's just due to this like dissolving like feature. Compare that to, again, the oil and water. Oil itself is like this super long carbon chain that has like some other like polar groups on the ends of it, but it is primarily just like carbons and hydrogens for the most part. And so that means that it's primarily experiencing just those London dispersion forces, which is not similar to the primary intermolecular force that water undergoes, right? So that's why they don't really mix. So, right, that's kind of a simplistic way to consider solubility. We can see some examples right here of like dissolving like kind of as a comparison. So what we have here are a bunch of different alcohols and their chemical formula and sort of model picture is shown as well. But for each of these, right, we compare the solubility of them in water and in hexane. Hexane is just C6H14, right? It's another long carbon chain. And what we can kind of infer from this table here is that for shorter alcohols that have like a smaller carbon chain, right, their dominant intermolecular force is hydrogen bonding. Even though they have that carbon to hydrogen bit, right, which is more dispersion type, the fact that they have just kind of a small carbon chain means that those dispersion forces are not as strong. And so because of that, right, the smaller alcohols are going to experience a higher solubility in water, a lesser solubility in hexane. For those longer alcohols, though, like pentanol and hexanol down at the very bottom, right, those really are dominated by dispersion forces. So in water, they wouldn't really dissolve very much. But in hexane, which is also very heavily just dispersion forces, right, they would dissolve a lot. So this is just kind of, again, like an example of like dissolving like and how we can kind of quickly predict maybe the relative solubility of different chemicals in different solvents. But so, right, that's just kind of like a brief overview of what dictates solubility in different mixtures. We're actually going to get like a much more mathematical approach later on in the chapter that I think will hopefully make it just a little bit more clear as to like whether or not a solute is going to dissolve in a solvent. But please let me know if you have any questions, and I'm happy to help.